Video 10, Generating Controlled Random Datasets. Previously we looked at importing image data into NumPy arrays. In this video we're going to take a look at using random variables, generating a time series plot and using different distributions. In this video we'll show different ways of generating random number sequences and word sequences. Some of the examples use standard Python modules and others use NumPy, SciPy functions. We generate artificial datasets using common Python modules. By doing so, we're able to understand distributions, variance, sampling, and similar statistical terminology. More importantly, we can use this fake data as a way to understand if our statistical method is capable of discovering models we want to discover. We can do that because we know the model in advance and verify our statistical method by applying it over our known data. In real life, we don't have that ability, and there is always a percentage of uncertainty that we must assume, giving way to errors. We don't need anything new installed on the system in order to exercise these examples. Having some knowledge of statistics is useful, although not required. To refresh our statistical knowledge, here's a little glossary we will use in this and the following sections. Distribution or probability distribution. This links the outcome of a statistical experiment with the probability of occurrence of that experiment. Standard deviation. This is a numerical value that indicates how individuals vary in comparison to a group. If they vary more, the standard deviation will be big. And in the opposite condition, if all the individual experiments are more or less the same across the whole group, the standard deviation will be small. Variance. This equals the square of standard deviation. Population or statistical population. This is a total set of all the potentially observable classes. For example, all the grades of all the students in the world if we are interested in getting the student average of the world. Sample. This is a subset of the population. We cannot obtain all the grades of all the students in the world, so we have to gather only a small sample of data and model it. We can generate a simple random sample using Python's module random. Here's an example of this. This is the code. This is a uniformly distributed sample. When we run this example, we should see something similar to this plot. Try setting sample_size to a big number, say 10,000, and see how the histogram behaves. If we want to have values that range not from 0 to 1, but from, say, 1 to 6 by simulating dice throws, we could use random.rand, int min.max. Here, min and max are the lower and upper inclusive bounds respectively. If what you want to generate are floats and not integers, there is a random.uniform min, max function to provide that. In a similar fashion, and using the same tools, we can generate a time series plot of fictional price growth data with some random noise, as shown in this code. This code defines a series of 100 data points, fictional days. For every next day, we pick a random value from the normal distribution using random.normal variate, ranging from mean_inc to std_dev_inc, and add that value to yesterday's price value, price_today. If we want more control, we can use different distributions. This is the code. It illustrates and visualizes different distributions. We start by importing the required modules and defining a number of histogram buckets. We also create a figure that will hold our histograms as shown in this line of code. To lay out all the required plots, we define a grid of 6x2 subplots for all the histograms. The first plot is a uniformly distributed random variable as seen in these lines of code. Notice that we range function in Python 3.5 instead of xrange function of Python 2.7. For the second plot, we plot a uniformly distributed random variable as shown here. Here's the third plot, which is a triangular distribution. The fourth plot is a beta distribution. The condition on the parameters is that alpha and beta should be greater than 0. The returned values range from 0 and 1. This is alpha and beta. The fifth plot visualizes an exponential distribution. Lambda is 1.0 divided by the desired mean. It should be non-zero. The parameter would be called lambda, but that is a preserved word in Python. The returned values range from 0 to positive infinity to lambda is positive, and from negative infinity to 0 if lambda is negative. Our next plot is the gamma distribution, where the condition on the parameters is that alpha and beta are greater than 0. Here's the code for the gamma distribution. Here alpha is 1 and beta is 10. Log normal distribution is our next plot. If you take the natural logarithm of this distribution, you'll get a normal distribution with the mean mu and the standard deviation sigma. Mu can have any value. Moreover, sigma must be greater than 0, as in this case, sigma equals 0.5. The next plot is normal distribution, where mu is the mean and sigma is the standard deviation as shown here. Here is the last plot, which is the Pareto distribution, and alpha is the shape parameter. This was a big code example, but basically we pick 1,000 random numbers according to various distributions. These are common distributions used in statistical branches, economics, sociology, biosciences, and so on. Now, when we run this code, we should see the differences in the histogram based on the distribution and algorithm used. Take a moment to understand these 9 plots. We use seed to initialize the pseudo-random generator, so random produces the same expected random values. If you want to prevent any repeatability of your randomly generated sequences, we recommend using random.system, random which uses os.urandom underneath. os.urandom provides access to more entropy sources. If using this random generator interface, seed function and set state function have no effect, hence these samples are not reproducible. Great! That marks the end of this video. In this video we've learned how to generate controlled random datasets. Awesome! In the next video we'll learn about smoothing the noise in real-world data.